Hi all. This is the first video of another type of applications based on derivatives. So far we looked into sketching of graphs using the derivative. So we looked into the use of the first derivative test and the second derivative test. So they were very useful, especially when we are sketching graphs, right? For for example, where the function is increasing, where the function is decreasing, and whether the function is concaving up or concaving down, and also the maxima, minima, and points of inflections were determined through first derivative test and second derivative test. So, and uh, and there are also higher order tests available, but uh, this is way beyond your scope. For now, we will only focus on the first derivative test and the second derivative test. So first and second derivative tests are used for graph sketching only, and that's just one of the applications, one of the many applications of derivatives. And this is the second type of application. The second type is the rate of change of a certain quantity that can be measured using the derivatives as well. So in this type of problems, and next we will look into the optimization problems. In both cases, we will only restrict ourselves to first derivative test only, right? So you just have to differentiate the function with respect to the given independent variable just one time, and this is much easier than curve sketching. Right, so we will only focus on practical application in this case, and so this would be interesting for you, and especially in the optimization section, we will look into more practical applications where yeah, maybe you are familiar with. Right, so the first thing, rate of change. So you already know about these rate of changes. For example, the basic one is the rate of change of the displacement, which is known as velocity. So how do you measure it? If you know the position of a particle at time t1 and the position of the particle at time t2, then you can find the average velocity by the change of displacement divided by change of time. So change of displacement divided by change of time. So this would give you the average velocity. Now, uh, this is okay. This can be used, but in certain cases, most cases, what we are interested is that, especially in the sciences, what we are interested is the velocity of a particle at that instance in space and time, right? So the average velocity, when you want to calculate the average velocity, you need you take 2 points, right? 2 points in space and time, which can be further away from each other or close to each other. It doesn't matter. But that would give you an average velocity, right? So from A to B, what was the average velocity? Now, what you're interested in finding the instantaneous velocity of a particle at that instant, right? At that instance means a small change in time, small time lapse is there. So when the time is too small, we need to take limits into account, and that's why we use the derivative test, right? Okay, so what I mean by that is that when a certain physical quantity, just like displacement, you can measure displacement, nuclear decay, flow rate, how flow of a certain liquid changes, the amount of flow of mass, how it changes. So that those can be measured. So when a certain physical quantity changes with time, so when this physical quantity changes with time, and suppose we can find a function between this physical quantity and time. So in that case, we can definitely derive that function with respect to time. So it's instantaneous rate of change. Suppose we can find a function between that physical entity and time, just a function, then it's instantaneous change at that particular moment, at that particular instant, is given by the derivative of that quantity. What does that mean by this? That quantity refers to this certain physical quantity with respect to time, right? So suppose, so these are certain applications. Example, velocity. If you want to find the instantaneous velocity of a particle at that instant, you can derive displacement, take the derivative of displacement with respect to time, provided you know the function between that quantity and time, the relation between that quantity and time. So if you can express displacement as a function of time, then deriving it is possible, right? So we will look into problems where the function is given, so you don't have to worry about that. Acceleration, if you want to know the acceleration at that instant, so you know that in that especially when it comes to rockets, its velocity keeps on increasing, and also the acceleration increases with time because mass keeps on losing on full, right? So the acceleration also increases. So a rocket has an instantaneous acceleration. So you want to find this. If you can find the displacement of the rocket with respect to a certain reference point, and if you can find the relation between the displacement and time, then we can find velocity of the rocket at that instance and also the acceleration of the rocket at the same instant. And also nuclear decay, especially when it comes to radioactive material, you know that radioactive material decays. So what is the rate at which the decay occurs, right? So that can be obtained by derivative of that quantity. I don't know whether you have seen this. So this is how you write the decay of a certain material. This is proportional to the number of particles at the moment. This is the amount of nuclear material there. So I don't know whether you have seen this. Maybe you have seen it in physics. Right? Then flow rate of a liquid. If you want to know how much liter, how much quantity of the liquid is being flowed through a pipe at a certain time, what is the rate of flow of that certain liquid, then you need the derivative, right? So these are the certain applications, and we will only focus on the first and the second one, and these are also easy, the same thing. You just have to, when the function is given with respect to time, you just have to derive the function with respect to time, right? So by doing that, you can obtain the derivative of that function with respect to time and use it to determine the certain quantities that you need. Now suppose x is an unknown. You can replace unknown with any quantity you like. Suppose x is a physical quantity and this x changes with time. So how do you write that? You write it like this: x is a function of t. So when you write it, it means that this certain quantity changes with time. So it changes. X is a function of time, which means it has a specific relationship to time. So when time changes, x also changes. So in that case, we can determine the rate of change of that quantity. How do you determine the rate of change of any quantity? Just find the difference of that quantity within the given time difference. So x2 minus x1 divided by t2 minus this one. So this should be the quantity at t2. This should be the quantity at t1. So this would give you the rate of change of, this is the rate of change of x. So in simple terms, we write it as delta x divided by delta t. Now this would give you an average value, average change, right? So what if you want to know the rate of change of that quantity at a certain instant? Then you need to change this. You need to take this difference to 0. You have to make this 0. If you make this difference smaller and smaller, what we are seeing is the rate of change of that quantity at a specific moment, specific time, right? Small time lapse is okay. So we treat them mathematically using limits. So if you take the limit, now if you take the limit of this 1 delta t. As delta t tends to 0, this would give you the instantaneous change because now this delta t is approaching 0, which means small difference. It looks like as if x had not changed, right? And this is the definition of dx by dt. This is the definition of dx by dt. Right. So keep this in mind. X here is any quantity, any physical quantity. It could be displacement, it could be velocity, it could be acceleration, it could be maybe mass, right? Or volume of a certain liquid. It could be volume of a certain liquid. It could be the mass of radioactive materials. Anything. Dx by dt. This would give you the instantaneous rate of change of x of that quantity. It's very important. Now if you can find a function, if you can show x as a function of time, then you know how to derive this. In that case, dx by dt is the derivative of this function, so the derivative is represented as f prime, right? Same things, it's very easy, right? So we looked into let's define what is instantaneous velocity, instantaneous acceleration, because we'll be using them, right? So when x is the displacement, so you know that we measure a displacement with respect to a reference point. Displacement is the shortest distance between 2 points, right? So displacement is a vector, you know this from physics. So if O is the reference point and x tells you the displacement of this particle with respect to O, so in that case x is the displacement and x is the physical quantity as mentioned here. Then dx by dt, this means the derivative O. Keep this in mind, especially when it comes to applied mathematics. And in applied mathematics under simple harmonic motion, we use this notation: simple harmonic motion and circular motion. In simple harmonic motion, circular motion, and also when it comes to pulleys, right, acceleration and all, we use this notation instead of dx by dt because it takes time. It takes a lot of space to write this. So instead we use x dot. If you see just one dot, that means it is the velocity. So I wrote it as v equals dx by dt. And dv by dt, when you differentiate velocity with respect to time, that gives you instantaneous acceleration. So here it means instantaneous velocity. So when you differentiate velocity with respect to time, that gives you instantaneous acceleration. So based on the displacement, that is the second derivative of the displacement with respect to time. So you can see d squared x by dt squared. This is the second derivative of the displacement with respect to time. Or simply put, x to double dot. Right? If you have two dots, that means you differentiate that quantity twice. So that's why it has two dots. That means acceleration. So keep this in mind. We will use these notations in applied mathematics. So a is equal to d squared x over dt squared or x double dot. Right. So suppose you know the function, you know the displacement of the particle, and with respect to time, you know a function, right? You know how displacement is related to time. So when the function is given, you should be able to get the velocity of that particle at the given time, or the acceleration of the particle at the given time, or both can be obtained. Right, so we'll look into some examples now. Right, so this is an example. The displacement, So the variable is named as x. Sometimes it will be named as r, v, h, anything. Of a particle is given by this. Now you can see x is a function of time. The relation is given to you. Find its average velocity during time interval from t equals 2 to t equals 4. And secondly, you have to determine the velocity at t equals 2. Now, when you ask to find the average velocity, that means the usual way of dealing with these average velocities, you just find the displacement at t equals 2, find the displacement at t equals 4, take the difference of the displacement and divide it by 4 minus 2. That gives you the average velocity. Now, if they say velocity at t equals 2, this actually means instantaneous velocity, because we are using preposition at. When you use the preposition at, means very specific, right? So how do you find the average velocity? The average velocity is very easy. So let's find the displacement x at time 4. X at t equals 4, say at t equals 4, what is x? So 4 raised to 3 minus 2 into 4 raised to 2 plus 1. So this is 64 minus, this would be 32 plus 1, that is 33. Some units, right? 33 units, because the units are not given. At t equals 2, what happens? So this becomes 2 raised to 3 minus 2 into 2 raised to 2 plus 1. So this is 2 raised to 3, so this would be 0 and plus 1 unit. So you can see at t equals 4, the displacement is 33 units away from the reference point. At t equals 2 is just 1 unit. So this is moving really fast, right? Really fast. Okay, I think my sum is right. 1632. Okay, good, right. So average velocity would be 33 minus 1 divided by 4 minus 2. Why 4 minus 2? Is t equals 4 and t equals 2. So say these are seconds, right? Seconds. So in that case, 32 divided by 2. So the answer is 16 unit per second, right? So this unit could be meters, centimeters, kilometers, whatever. Right? And the second one, this is for part A, and for part B, instantaneous velocity. To find the instantaneous velocity, take the derivative. Dx over dt, the derivative of this would be 3t squared minus 4t, that's it. Now this gives you the derivative, the velocity of that particle at any given time. The time is not specified here, right? It's general time. And if you want to find the velocity of the particle at t equals 2, all you have to do is to replace all t variables with 2, right? So how do you write that? At t equals 2, dx by dt would be 2 squared minus 4 into 2. This is 12, 12 minus 8 is 4 units per second. You can see at t equals 2, the velocity of the particle is 4 units per second. Even they are not asking us to find the velocity at t equals 4. Let me find the velocity at t equals 4. It doesn't take much time. All we have to do is to replace t by 4. So 4 squared minus 4 into 4. Just wanted to check what the value is. 4 squared is 16. This is 48. 48 minus 16, that is just 32, right? 32 units per second. Now you can see why. At t equals 4, the velocity of the particle is 32 units per second. At t equals 2, the velocity of the particle is 4 units per second. Now you can see, as the time increases, the velocity of the particle also increases. Now you can see that you can see whether the function is increasing or decreasing by a simple test. You can find the critical values based on this derivative and check the interval of time where the function increases or decreases. So I can take t outside. If you want, do not write this. So if I take t outside, this would be t 3t minus 4. 4 divided 0 and 4 divided by 0 and 4 divided by 3. So 0 and 4 divided by 3. This is a minima function. So minima means in this, between this is negative and this is positive, right? So what does that mean? The function is decreasing from 0 to 4 by 3, and beyond 4 by 3 the function is increasing. So the particle, the velocity, right, that function is decreasing. The velocity sorry, not the velocity, yes, actually, yeah, we could say velocity is, in this case velocity is negative. Velocity is negative means it's coming towards the reference point. It's like that. And after t equals 4 by 3, the function is increasing. The derivative is also positive. Function increase means again it is moving in the given direction. Okay, so this is something extra. You don't need to worry about this one yet. And I just wanted to find what happens at t equals 4. If you want to find the acceleration, then you just have to derive this twice. Derive this twice, derive it again, and then you find the acceleration, and you can find the acceleration at any instant.